Welcome back to Neural Intel, the place where we get right into the technical details of AI and machine learning. Today, we're exploring a completely different paradigm for computation, neuromorphic computing. And this isn't just some new software. We're talking about a fundamental rethinking of computer hardware, inspired by the most powerful and efficient computer we know, the brain.
So let's just start with a number, 50 milliwatts. That's the power a tiny cockatiel's brain uses. Now, to put that in perspective, your phone's processor can burn through thousands of times that amount. And yet, on that minuscule power budget, this bird can navigate complex environments, fly at 20 miles an hour, and even learn human words. I mean, that's just a stunning feat of engineering that our very best, most power-hungry supercomputers can't even begin to match for that combination of speed, size, and efficiency. And this massive efficiency gap is exactly why researchers are turning back to biology. The goal here isn't just to mimic intelligence anymore. It's to actually reverse engineer the brain's fundamental principles and forge them directly into silicon.
And as Mike Davies, who directs Intel's Neuromorphic Computing Lab, puts it, the goal is to, quote, understand the principles of brain computation and map this insight into chips. Now, this vision isn't exactly new. Pioneers like von Neumann were deeply inspired by the brain. The difference is, now we finally have the technology to actually build it.
So, to really grasp the technology, we have to start with the biology. Let's take a look at how neurons actually talk to each other. It really all boils down to a four-step process. First, you have these voltage pulses, or spikes, that arrive at connections called synapses. Second, the neuron's dendrites, they kind of aggregate all this voltage. Third, if the combined voltage at the cell body, the soma, reaches a critical threshold, boom, an output spike is generated and sent right down its own output channel, the axon, onto the next neurons.
Okay, the principle at the very heart of all neural communication is the spike. Think of these as the currency of information in the brain. But here's the key. They are completely binary. They're all or nothing events. This means the information isn't encoded in their size or their strength, but in the precise timing of when they occur. And that is a critical distinction from conventional computing. It changes everything.
And you can just forget the neat, orderly layers of conventional deep learning. Biological networks are, well, they're messy. Each neuron connects to roughly 10,000 others, creating this incredible web of feedback loops. Computation isn't some linear calculation, it's a dynamic flow of energy. The result just emerges from countless local interactions, kind of like ripples forming in a pond.
So this biological blueprint, it doesn't just suggest a new algorithm. No, it demands a radically different way to build a computing architecture right from the ground up.
And that brings us to our neural signal check. Here's why this development actually matters at a technical level. We are shifting away from brute force. Instead of processing these dense arrays of numbers like pixel values, information is now encoded in the timing of sparse asynchronous events. This is the absolute key to unlocking the brain's incredible efficiency.
All right, so theory is great, but let's make this really concrete with a practical example that every AI developer knows and loves, recognizing a cat in an image. And this just illustrates the fundamental difference perfectly. So conventional AI processes a full static image frame, a big, dense grid of pixels, and it relies on raw speed to perform a massive number of calculations. The neuromorphic approach, on the other hand, is completely different. It processes a sparse pattern of spikes that encode only the key features like edges and motion. This pattern gets sent in parallel to thousands of neurons that are simply waiting to recognize a specific temporal pattern.
So the crucial point for anyone in deployment is right here, the memory bottleneck. Conventional systems are fundamentally limited by the memory interface, how fast they can stream those large matrices from memory to the compute units. It's a sequential problem, a traffic jam. Neuromorphic systems, because they're parallel and event-driven, completely sidestep this bottleneck. This gives them a huge advantage in both energy efficiency and low latency.
The system even has this incredibly elegant efficiency trick baked in. As some neurons start firing, recognizing a feature of a cat, a feedback network senses this. And once a result is certain, it broadcasts a stop message to all the other neurons. This is basically power gating, shutting off power to the parts of the chip that are no longer needed, saving immense amounts of energy.
So how does all this build towards real-world enterprise applications? Because, this isn't just a research curiosity.
Well, the implications for enterprise deployment are pretty significant. We're talking ultra-low latency, which is a game changer for robotics that need to react instantly to the real world. Extreme power efficiency finally allows for powerful AI on tiny, battery-powered edge devices. We could even see future sensors that think, generating spikes directly and saving massive bandwidth. And because it avoids that memory bottleneck, the entire architecture is inherently more scalable.
This leads to a profound shift in how we even define computation. A result isn't the output of some pre-written program. Think of it again like dropping that pebble in a pond. The input, a stream of spikes, it disrupts the network. The answer isn't a number at the end. It's the new pattern of ripples the network settles into. The system literally finds its own answer.
So, what becomes possible when computation is an emergent property, not a programmed instruction? What does it mean for us as developers and engineers when a network can self-organize to solve a problem, reconfiguring its own parameters until it finds a better, more adapted state? That is the fascinating and challenging question that neuromorphic computing forces us to ask.
That's all for this deep dive. We'll explore how these concepts are mapped into actual chips in a future explainer. To stay updated, visit us at neuralintel.org, and you can find the Neural Intel podcast on Apple Podcasts. Thanks for joining us.